Hey guys, so we've got a few things to go through today. The first thing I'm going to do is do a bit of a deep dive into looking at all of the things we do and to make up one frame of Starter Citizen. And as you all know, we use Lumberyard as our base engine, but we have some different requirements to Lumberyard, so I'm going to particularly point out the things that we've had to extend and build on top of Lumberyard. After that, I'll go through some of the recent updates we've put into the 3.0 that will be in your hands soon, and then touch on some of the graphics roadmap that's coming up. Dive into some CPU parallelism, which goes back to what Chris was talking about with Intel earlier, and then talk about some of the mid to long-term goals we have in the graphics and the tech department. So just to start you off, I'm just going to give you a quick video to show you all the breakdown of one frame, and then I'll go through and explain what is you're seeing on screen now. So then, there's quite a lot to go through there, so I'll try and get through all of it in time. So the first thing we do is not too exciting, but because we have these procedural planets now and all this procedural content, we can't possibly bake the lighting for all of these locations. So our first job is to bake an environment probe for that location that you are currently stood at on the planet or on a moon, or even in space we still have to do this. So this is a render, 6 different angles of the local environment. And then we have to process this and blur this and compress it all on the fly. And this all happens at the start of the frame. Now, this is quite complicated, takes quite a while, so we split the work up. So this one texture you're seeing here actually is spread over 20 frames to process this thing. So every 20 or so frames, we can update the localized lighting to give you reflections from your ships or nearby objects. After we've done that, next job is to do the shadows. Now, what you're seeing here is what we call our shadow pool, which looks a bit weird, but it's 8K texture, and it's where we pack all of our shadows in. So here, there's about 6 large shadows, and there's a whole bunch of little small ones crammed in up there. So this is something we've extended from Lumberyard. We needed quite a lot of variation in our quality for our shadows. Sometimes we need 4K shadows for cinematics, especially for Squadron or something like that, or any type of close-up conversation. And then at other times, we're looking at Levski or something where there might be hundreds of lights, and we might need 30, 40 shadows at once. So this system we have allows us to vary to get the high quality when we need it and the spread of lots of lights when we need it. OK, now we're on to the actual frame. So the first thing we do, just for pure optimization, is to render out everything that we think is going to block something else in the scene. We want to keep the cost down as much as possible, so we have to try and pick what we think is a good occluder. So we find the big meshes, the ones without too many vertices, the ones that are close to the camera. We do a cheap shader, and all of them get rendered first. So that's what you see in here. And then at the end of the frame, we also read this back onto the CPU, and we actually use that to do an extra set of culling on the CPU spread across multiple cores where we can avoid a mesh even getting to the GPU the next frame, which is obviously best optimizations not to do any work in the first place. So that's what we aim for, but this also gets used on the GPU to hide all the meshes that are behind. After that, we start our actual material rendering. Now, this is just a tiny subset of the textures we use on one material, but we can have like up to 15 or 20 textures on one material. So this is, starting from the left, it's our albedo, which is our color, basically, our normal maps, a smoothness map, a blend map, and a height map. And you typically have this set of textures twice for one material, but some of our materials have 4 or more layers, and the planet can have up to 12 layers. So now we're on to actually rendering the scene. So we don't actually render color. We actually render into what we call a G buffer in what we call the Z pass, which is where we write out material information, like in this case, the normals, which means the direction that the surface is facing. So as well, it looks a bit abstract. And then we actually also render this in multiple stages. So we start off with the planet geometry, which is what you see in here. Put in all of our instanced objects, which here is rocks and some asteroids in the distance. And then it's all of our static objects, and then our dynamic objects and our characters, and then also our decals as well. And the ordering is really important, so we can composite everything correctly. For example, the decals might be like mud or dirt or something. You'd want them to apply to your static geometry, but not to apply to your dynamic geometry. They have a different system for handling that. Okay, after that, at the same time, we're rendering to about between 3 and 6 textures at once. So this is the next texture we're writing out, which is the albedo, which is a fancy word for color. We've got smoothness, which is how opposite of roughness, just how rough a surface is. The white areas are the smoothest. We've got reflectivity, which is based on the index of refraction or how hard a surface is. So all of our metals will appear bright white here, and all of our non-metals will appear a dark shade of gray. Here is the hue of the surface. It's not showing too much interesting here, but if you had like a gold or a brass, something that has a particularly colored reflection, it would show up in this one. We mask out some special materials, so you can see the guy's face. It's got a mask on it, and we've also got the planet terrain. We do some special effects on the surface of the planet, so that needs a special mask. And then a bunch of extra material properties. Now, these can vary per material, so on the face, it tells us how much subsurface scattering to do to simulate the skin, and then we use this buffer to store other miscellaneous data we might need for whatever material we're currently rendering. Okay, and now we're on to motion vectors, and this is what we use for our motion blur and also our anti-aliasing technique. There's not too much going on here because it was a fairly static scene, so the guy has obviously got I'm not sure if there's any variation in him, he's pretty flat at the moment. And there's the planet in the background, which also is a dynamic object, obviously. So that's got some motion vectors. But the rest of the screen is just black, which is because we know that we're stood on the planet, and we know that the static geometry on the planet must be moving just at the same pace. So we don't actually need to write anything out for them, and that's a bit of an optimization. And the last texture is just the emissive, anything that glows or has any bright surface. So we've got some headlights on the helmet, and we've got a few things on the speeder bike, and then we've got the sun. Okay, after that pass, we start doing all of our first stage of post effects. We have 2 stages of post effects, and for the first one, the first effect is to calculate the atmosphere. This looks a bit abstract because it's not actually the color of the atmosphere, but it's just a pre-computation to work out how we will do the atmosphere later and apply it at a later stage. This is something that was done by the Frankfurt office, the atmosphere, and the results seem to gain a grade. It's great to be able to fly up to the atmosphere and see from every angle all the different colors you get. After this, we've got the shadows. So we saw the shadow map earlier, which is a view from each light of what the scene looks like from their perspective. Now we have to apply them to the screen. So we actually render 5 different shadow maps for the sun. This is the first one. And as we go further out into the scene, we layer up more and more distant but low resolution shadows. And then next stage is we have to composite all of the other point lights in the scene. So this is the sun shadow, and this scene's got a couple of extra lights in it. But we can have up to 12 shadows all layered on top of each pixel, so 12 shadows per pixel, and as many shadows in the scene as we want. After that, we've got the occlusion. So this is something that the Frankfurt team have just upgraded. So the way we calculate our occlusion is if you imagine for every pixel you had like a small cone that was sticking out from the surface, we try and work out which direction it would point if it was going to point in the direction of least occlusion. So in the center of this table, it would be pointing straight up. But say in a corner here, it would be pointing diagonally. And this is a visualization of that direction. You'll notice it's pretty noisy and patchy in places and has some weird artifacts. So we do a smoothing pass to get rid of all that, but that's basically there as an optimization. We can't afford to do the full occlusion calculations at every single pixel, so we type of mix and match. Each pixel does a slightly different calculation, and once we blur them all together, we get the correct result. This is another part of it. This is rather than the direction of the cone I was talking about, it's how wide the cone would be. So from this table, we've got 180 degrees of unoccluded, whereas, say, in a corner, you have 90 degrees of occlusion, and then in a crevice, you would have even less. So it's the same thing here. We apply a smoothing pass to get the quality higher. And OK, now we're on to some of our lighting. So this is the first stage of our lighting. This is our screen space reflections. Most games do these effects now, so they're fairly standard at this point. There's not a huge amount of reflective surfaces on here because it's on the planet. There's actually just a mirror just out of shot below the guy's foot, which we'll see later. A little bit on the top of the spaceship as well. We do these by tracing little steps across in screen space to try and find something that looks like it might have reflected from a surface. We can't rely on it too much because obviously it's based on what you have on screen. So anything that is off screen, we can't detect, and we have to use other techniques for them. OK, so now we're starting to look like a bit more of a game. So this is our opaque surface lighting pass. This is a hugely complicated shader that we spend a lot of our time on. And it combines everything you've seen up until this point into this one image. So that's our environment probe, our shadow mask, our Z pass, all their material properties, screen space reflections, the occlusion. That's all applied here in one giant shader. So this is something that has been extended quite a bit from Lumberyard's implementation. We have a bunch of new things like area lights or rectangular area lights, and a bunch of other features that Lumberyard didn't come with that we felt were really important. The area lights, for example, is something that artists were crying for because in a sci-fi environment, it just is totally typical to have like those long, stretched aerial highlights everywhere. And one thing you'll notice is the guy's face is looking a little bit odd. The reason for that is we do something special with the face for subsurface scattering to simulate how the light enters your pores and then is scattered through the blood in your veins. So at the moment, we're only seeing the reflections from the face. We haven't actually got the main lighting. And this is a separate pass to do this is the incoming light to the guy's face. And then we do this simulation, a screen space simulation of the subsurface scattering. So once we've done that simulation, which is hard to visualize here, but once we've done it, we composite it back. Now we get to the final lighting result for the opaque scene. So we're looking pretty good at the moment. You'll notice the colors are a little bit odd, and that's because this image is still in HDR space. So the whites are extremely bright, and the darks are way too crisp and dark. So we need to turn that into a low dynamic range color space later on. So that comes later, though. So first, we've got to start applying all of our transparencies. So the first transparency we have is the fog system. So this came from Lumberyard, the base implementation. It was a really powerful effect. Our artists were absolutely over the moon when we got this thing in. So this is a bit of a weird visualization, but it's showing you top-down type of what the fog looks like for one slice of the fog. So it's actually a voxel simulation that runs in a certain distance, a fixed distance from the camera. And you can see like the blocky cubes in here. You don't actually see this cubey problem from your perspective, because if you imagine we're at the bottom of this frame looking up, it's type of the blockiness is in the depth, so you don't really perceive it from the camera. So the next stage is to light that. So this is injecting the light into that, and you can start to see some shadows appearing in it and some shape appearing over near that bike. And then we apply it onto the screen. It's a bit difficult to see at the moment, it's still quite dark, but you can see the haziness and the glowing around that. There should be a slight glow here, but we'll see this a bit more later on. OK, now we start layering on our transparencies. So we've got these rings around the planet, we've got particles. We'll bring them in one at a time. We've got the visor on the glass. OK, and then once we've got all the transparency done, now we need to enter our second phase of doing the post effects to try and bring the quality to the final image quality and sort out these weird colors we've got. So the first stage of this is our optics system. So we're quite proud of this. It looks really great. It's something we implemented early last year, I believe, and we had it on one of the ATVs, so you might have always seen it, but I'll go a bit more into the details here of what's going on. So optics were really important for us because two reasons. One, we have, it's a sci-fi game, and everyone knows that we have these J.J. Abrams style flares everywhere, and the contrast in space when you're stood, say, on a moon, which might be brightly lit, but there's no atmosphere and it's pitch black above you, the contrast is just enormous between the brightest and darkest area. And this is something we wanted to simulate properly. We didn't want to fake it or try and crush the range like you might typically do in a game. We wanted to keep the full dynamic range almost as high as the eye actually perceives, which is a crazy large range, but we're almost there. So the first stage of that is we start downsampling the image to try and build these different, we call them bitmaps, smaller versions of the image. And the reason we do that is for performance. We want to be able to, say, blur or stretch, like, say, the sun might want to produce a flare on the opposite side of the screen. And if we need to do such a large effect, we need to run it on a low resolution so that it doesn't cripple your GPU. So here we start making blockier and blockier versions. And we really go down to like a really tiny image. The bottom one's like 16 pixels wide or something. OK, and now we've got them images, we start doing the fun stuff. So the first one is the J.J. Abrams effect. So we go horizontal, and then you'll see the last one. This is what it looks like just stretched, but it looks a bit weird. So once we re-level that image and darken it a little bit, then we get this nice horizontal streak. Oh, well, subject to your personal views on J.J. Abrams. And then next stage is to do the type of lens flares. These are the bit I really like. These are physically based. We have 4 different type of lens distortions we approximate or simulate. And the artist can choose how many of each type of lens distortion they want. So they can say they want 10 elements on the screen, and this one should have 20% of this distortion, etc. And it's quite sophisticated. So they can really build a different palette of lens flares. So this one is that you can see the sun has started going to a weird shape, and it's got this, these colored hues around the edge of it, which is a chromatic aberration, which happens on, well, the cheaper the lens, the more you get this. Once we darken it down, it starts to look a little bit more interesting. Still a bit weird at this point. We do a slight blur to soften it out, and also to approximate artifacts in the lens. And then we repeat this for a bunch of different shapes and sizes, depending on what the artist wants. And then we just start compositing this thing together with all of the different elements going into one nice giant flare. So we're quite proud of this. We'll see what it looks like composited in a minute. But the main benefit of this system is because it's fully procedural, it's based on whatever the image we've rendered prior to this point. So it's not like the artist has to say exactly how this lens flare should look on this particular light. It just, whatever image we get, it will generate lens flares as a real camera would do, which means things like the shape of your light really make a difference to how the lens flare will appear. And it also means you don't have to have an actual light source, just a light bouncing off a table or something, or a fire, or an explosion, or a laser bolt. All these things can produce lens flares. So it's much more dynamic. You get a lot more interesting effects from it. And it doesn't have to be these type of crisp flares. You just get a bit of glare as well. So if you're on like a moon or something, you'll get the glare coming up from the moon, which look quite nice. The final advantage is, because none of it is based on the actual scene content, like the artist doesn't have to manually specify these things. It means that the art directors can come in later and totally repurpose and restyle the game by just changing the lens flares. So with the scope of our game, that's really important to be able to quickly manage all this content, because there's a huge amount of content in here. OK, and the final stage of the optics is to apply bloom. This is fairly standard. Most games do this in the same way now, but it's also physically based and also a replacement for lumberyards. Color correction is next. This is a bit of an odd image, but this is what we call a LUT, a lookup table, where every single color is represented here, and it's a remapping. It tells us how to transfer from the color that we had in the first render into what the artist actually wants. So it allows them to change the hue or contrast, saturation, things like this. Now, the last bit of the optics that we're proud of that I didn't mention was this one. This is the exposure system, which is something that's quite new to us, and it's still being refined a bit. The planets and the moons really push the exposure system to its extreme, so we're quite proud of this. We generate a histogram of the entire scene, and we have to analyze how bright the scene is, and not just, most games would just look at how averagely bright the scene is, and then they would adjust the image to compensate, so that, like, to approximate what you'd get in your eye. But we go a little bit further because of the extreme contrast we have in the game. So we actually simulate 2 different mechanisms. The first is your pupil response. So your pupils can open and close from about 4 millimeters to 8 millimeters, which gives you a dynamic range of about 2 to 3 stops on a camera. So we have that, and that can bring you very quickly from a bright to a dark scene. But it's got this limited range, so it can't take you from an extreme. So if you walk outside from an dark interior like this to bright sun, you'll get a bit of an effect, but it won't be enough. And that's where the second stage kicks in, which is our rod and cone simulation. which does the much longer type of exposure and has a much wider range, but it takes longer to do it. We don't go to the extent of real life, which can take 40 minutes to adapt to the darkest surroundings. We crush that down to about 20 seconds, so you guys don't get bored. OK, so now we have to put all these optics together. So this is our high dynamic range input we saw before. And then we apply all these bad boys, and we end up with this, which is starting to look a lot nicer now. So we've got the flares, the colors look a bit better, and yeah, generally the colors aren't as the darks aren't as dark and the brights aren't as bright. Everything's a bit more representable on a normal monitor. OK, so once we've done this, we now have to clean up the image. So SMAA is an effect that was already in Lumberyard and in CryEngine before that. It does a good job. It basically finds all of your jagged edges. It classifies them into different types, like a left-hand corner, a diagonal, or whatever it might be. There's quite a few different classifications, which are represented by the colors here. And then once it's worked out what type of jagged edge it is, it applies effectively a smart blur. It tries to fill in the gaps and soften that edge to get the correct result if you would have been rendering at a higher resolution. So if we go from pre-anti-aliasing to having it turned on, I think if you look, say, on the left of the character's leg, it does a really good job at softening that up. What you'll notice is, even though it looks great on the character, some of the areas like this crate still have significant banding and jagged lines on them. And I think there's a few other examples over on the bike over there. So we've recently just introduced temporal anti-aliasing to hugely improve the results of this, which is something we've been suffering from for a long time with the anti-aliasing on this game. So if you look between the two now, say on the crate, it completely cleans up everything that's left on that, and we end up with a really nice, smooth image. So this is something that's just going into 3.0. And the good thing is it's no slower than what we had before. The performance is almost identical. We're still iterating this. We're going to continue to iterate it. But the engineer that's doing it is really talented. And we've taken it one step further than what we have here actually now, in just in the last few days. And temporal techniques basically work by looking at the previous several frames of motion. And in our case, we look at 4 frames prior, and we work out from them previous 4 frames what the results should have been there. So we wobble the image ever so slightly, which is imperceivable to you, and then over the 4 frames, we work out what the details should have been in that 1 pixel, and we can recover that and get a nice soft result. But the problem with using the previous 4 frames, well, there's all sorts of problems, to be honest. It's caused us a lot of headaches. So we have a lot of moving objects, obviously. We've got spaceships that move. We've got planets that are moving. We've got all sorts of things going on that we might not have in a normal game. And we also have a UI, transparent UI, a transparent glass screen, a transparent visor. All of these things make it quite difficult to account for the previous 4 frames motion, because your visor might be spinning this way, your cockpit might be going that way. There's all sorts going on. So we've recently done a change that hopefully will work around them. But yeah, you'll be able to see this in 3.0 once you get your hands on it. OK, so that's our final frame. Looking nice, I think you'll agree. So I'll take you on to the next bit. So just to go back over some of the updates we've had. So some of this is not just the UK graphics team, but the Frankfurt engine team, which have done a lot of good work here. So the first one is the P4K system, which is our new data delivery system. It's something we use internally and externally, and it means the time to get a new build is vastly faster than it was before, like undescribably faster. So we're really happy at that. Basically, the way it works is rather than having a few giant data files, we just have one enormous data file. But the delivery system actually goes in and finds the individual assets that need to change and only transfers the smallest part that actually needs to be sent. So we can get patches in seconds where we would have been waiting hours in the office, or a 20-minute might be a typical build download. Now it could be 10 seconds. So we've changed the compression we use on this. And we've also added a dedicated SSD streaming path, which allows us to transfer multiple files at once. So yeah, this P4K system has been a huge benefit. And I think you guys will appreciate as well when you get any patches from 3.0 onwards. You'll notice a significant difference in the amount of time you sat there waiting for it to download. Next one is the service performance improvements. There's server performance is something the Frankfurt team have really been concentrating on lately, even in the last week when we've been out in Ivakati. The results they're getting is they're getting quite a lot of significant improvements, so we're really happy about that, which obviously translates to less type of jittering or any type of network bugs. We've got planetary rotation, something we've recently been putting in, which has been quite a challenging topic, to be honest. A lot of text relies on things staying still. And like I said, with the temporal anti-aliasing, we expect the floor not to be moving, but now everyone's moving at 1,000 miles an hour, no matter where you are. But yeah, it's cool. You obviously get the changing light conditions. The sun is never still, so that's really nice. I think the time is accelerated, though, so you don't have to wait 24 hours to be able to see a sunset, but render to texture is something you might have seen on ATV. It's actually, there's an example of it here, of this hologram on the right-hand side. The render to texture is used for holograms. It's used for all of our UI screens now. It allows us to embed content into the world from another location or like a 2D set of graphics onto like actual in-world things like the glass or holograms and stuff. And yeah, it's been a great help to us. Next one is the temporal anti-aliasing, which we've just seen. The improvements to the SSDO, which I'll show you a little bit more of in a minute. We've improved the color correction, which is our tone mapping curve. And finally, we've started work on a new suite of shaders that we're trying to go more physically based on our shading, but we're also trying to bring in more gameplay-driven shaders. So when you have things like damage on a shader or dirt, and if you've like been on a planet, or where if you've been using the item or object for too long. So all these things we want to have a visual representation on. So our first version of these shaders is the physically based glass we've introduced, which I've got a quick demo of. But that will continue after 3.0 when we go through all the materials, eventually upgrading them. Okay, this is the occlusion effect. So this is our occlusion turned off. This is our previous occlusion, if I just go back and forth then. So it adds quite a bit of detail, quite a bit of shadow. But our new one, so it's different, but it's type of more contrast. You get like you don't necessarily get more shadowing, but you get shadowing in the right places, and it's a deeper shadow. And if you look at like Mark's chin, or on his like the side of his nose, and next to his eye, there's a lot more detail in the new version. So we're quite happy with that, but that's something we're going to continue improving in the coming release. So we've got our tone mapping, which is how we take the HDR colors and convert them to low dynamic range for your monitor. So if you look at this very boring sphere here in the middle, it's got quite a muted shade on the right-hand side of it. It's the old tone mapping is crushing the colors a little bit too much. It's not quite vivid enough for artists. They like to call it pop. It doesn't pop. So the new version is a little bit more vibrant, a little bit nicer, and it follows industry standard ASUS tone mapping curve, which is, but we've made a few tiny modifications, but we're really happy with the colors. Okay, onto our shaders. So if I just play this video. So like saying, this is just an example of the canopy of the Gladius, but we've done it's one of the first of many shaders we're taking a pass on because some of them are starting to get a little bit old in the tooth and need a bit of an upgrade. This glass has things like physically based refraction on it. It simulates like the color shifts you get from like a glass when it's type of greasy. There's all sorts of nice joys in this thing, which the artists can't wait to get their hands on. Just to give you an example, this is the old glass we had, which just looks like something that's clean and transparent, not much going on, and the new one is significantly more interesting. Now, obviously, this is my program art. Once it gets into the artist's hands, which it was only completed this week, they're going to start doing some much nicer stuff with this, and hopefully getting some of the ship's glass looking better for 3.0. Just to go through some of the effects. So here is like the thin film effect I said, that it gives you a slight hue on the reflections. We've got refraction, transmission if you want colored glass, dirt, which is one of the things I said we want some more gameplay interaction. And then here's an example of like a cracked piece of glass. This one's quite nice. When you get the side angle, it shows you that the cracks actually have some 3D to them. This is something Chris and the artists have been asking for a long time, a very long time, but they're super happy they're about to get it now. Yeah, with the physical simulation going here is quite involved just to get this, but it looks really good, and we're really happy with this. Okay, so just a quick talk on what's to come then. So on the graphics side of things, we've got new hair coming along. There's a lot of work we want to do on the terrain and then on the occlusion. We've got these gameplay-driven material shaders I just mentioned. We've got glass clouds, also known as space fog, so we can do things like fog and asteroid fields and stuff to make it a bit more interesting. We've got a new shield effect on the way, which is going to use our new GPU particles, which work's just started on this last week. We've got some depth of field improvements that are coming along nicely. Color processing improvements, we've got quite a lot planned there. We want to really improve the color reproduction and get the result on screen much more faithful to what the artist originally produced in their packages. We've got the motion blur improvements, and then finally complex shading models, which allows you to do things like a clear coat, which is what on a car to get like the car paint effect. And yeah, something the ship guys, and particularly the armor and things like this, they would really enjoy having a bit more complicated shading on them. Okay, I just wanted to briefly touch on something else, which was CPU parallelism. So obviously, modern games are putting huge pressure on CPUs. We're no exception. We're actually pushing the CPU pretty hard. The gameplay code is got a hell of a lot going on there. So and the rendering as well, and all these different systems we have, like I don't know, the things that Eva was showing you earlier with the animation. We've got the facial animation system. All of these things are just adding to the cost of the game. So multi-threading is a massive part of getting our game to run well, and we use it quite a lot, and we're using it even more lately to try and get the best possible performance. So our Frankfurt team are leading the charge on this. Our principal engine programmer, Chris Bolte, is pushing forward with this. And we've got two main systems we use to get the performance great. So we've got our batch updater and our background workers. So yeah, our batch updater is basically, it's where we have a lot of the same work to do. So we want to cull 1,000 objects, or we want to update 50 thrusters, or something like that. So the batch worker gets one job with lots of different elements to it, and it gets all of them done, and it spreads them across all of your CPU cores at the same time. And that's been a huge benefit for our gameplay. Like it's very easy to take all of our, like I said, our thrusters or something like that, and then we can just batch them all in one go. And we get some huge performance wins from this. So a lot of the game code has been made to make use of this now, and it's been the bits that haven't been have been converted over. So this has been a huge improvement lately. And then the other mechanism we have is our background workers. So these do stuff that we don't need as immediately. And so say something like the streaming system, we need to stream in a new texture or a new mesh or whatever it might be, or some audio. And that doesn't need to happen immediately, but it needs to happen gradually over time. So these background workers, they kick in whenever the batch worker isn't busy. So they have been programmed a very smart way using fibers. That means they can kick into action as quickly as possible to try and fill all the gaps between all the work that the background work, sorry, what's it called? The other ones are working. Make some words. Yeah. So, okay, and something else to mention, which goes back to what Chris mentioned earlier, is the background workers are really tightly coupled to our I/O system now. So, in the case you have an SSD or Optane, we can read multiple files at once, and we start decompressing them the second one chunk of that file is loaded in. So we actually are processing up to, say, 4 files at once, and we can be decrypting many files or decompressing many files at once, depending on how many CPUs you've got. So these two systems together mean we can get data off the disk extremely quickly, which is really important for us because of the vast amount of data we have in our game. Okay, and just before I finish, just one last slide, just to talk about some of the things that are on the horizon and we're hoping to get onto soon. So object container streaming is something you might have heard of on ATV. It's type of each chunk of our game, rather than a level, which makes no sense for something like us. Each like the interior of a spaceship will be an object container. A space station might be an object container. A single shop in a space station might be an object container. This is type of the unit we use to build our solar systems. And we're working on the streaming support so that we can very quickly load and unload these things dynamically without affecting the frame rate and without a hitch. So that's in progress. The planet effects. So we've got all sorts of things we want to do on the planets. Some have been started, some are not so soon, but we've got things like improved shadows, like a bespoke system for shadows. Clouds, you've probably seen some demos of the first version of the clouds. There's something we want to continue working on. And there's many other things on the planets, like roads and other such things. And then in space, equally, we've got things like stars, the sun, and rings around planets. We need to get all of these effects improved. We've got some of the basics in for them, but there's a lot further we want to go on that. And then dynamic global illumination. So we have this on the planet with the environment probe you saw at the start of the presentation, but we need something equivalent for the interiors so we can accurately update the lighting. And this is crucial because we want to be able to shoot out individual light bulbs in rooms and have all the lighting correctly update. And we can't just tint the lighting or adjust it and fake it. We need to actually recalculate everything from scratch. And the reason it's more complicated interior versus on a planet is just because of the number of light sources that are involved. We might have, like, in a room like this, might be 50 light sources in the room, and to calculate all that, while somebody sat there shooting all the lights out of a machine gun, there's quite a lot of optimization needs to go on there. And then next few things, so we've got to use the batch workers we talked about earlier. We've got 2 threads we run, 2 processes that compute the rendering and the physics, and they're still done without the batch worker. So we need to convert them over so we get some extra performance wins. And then when we've done the render one, when we've finished that off, that's what's going to enable us to really take full advantage of something like Vulkan or these new APIs that really let us, on the graphic side, like spread the work across as many cores as possible. And that's where we're really going to get some real performance wins. OK, and that sums it up. So I'll hand over to Brian. Hope you enjoyed.
Thanks, Ali. I don't know about you guys, but it's like a wall of information, right? Luckily, these will, they'll be on online, so we'll be able to check them out and actually see it a little bit slower if we want to. So, cool. Now we have time to open up to a Q&A. If you're cool with that?
Yeah.
Awesome. We'll take questions from you guys in the audience. I think we have some guys with mics around. If anybody's interested, you can just raise your hand and we'll run up to you. I'll start off with the first one, very generic, as always. As far as tech goes and what you're involved in, what would you say would be one of the most unique challenges for Star Citizen and the work that you need to do?
Unique is probably the scale. Compared to everything I've worked on previously, the scale in type of 2 aspects. You've got the physical scale, obviously, solar systems and planets, and everything is ginormous. And dealing with all that and having all of our effects work on things like rotating planets and the loading of all this data and managing all the data is like a huge challenge, which normally get these little confined levels where you can type of assume a lot. And rendering is all about assumptions. You make some assumptions, and that's how you get the frame rate. And it's very hard to make assumptions on you've got a completely sandbox, open universe. And the other part of the scale is like the gameplay. Obviously, you can't assume anything is fixed. You can't assume anything is going to stay looking like it's going to look. Something might be there a minute and then destroyed the next minute. Everything's type of dynamic. There's so much dynamic, emergent gameplay. Again, it stops us being able to assume anything. So then we have to be much more creative in how we can make things fast and look good while still supporting all of the great features there when obviously once.
Yeah, I've heard that actually across other disciplines as well. And it's true. I mean, with just the vast scale, there's so many other things we need to keep in mind when we're crafting something as opposed to a small little area or so on. Anyone have any questions from the audience? Whoever has a mic, somebody up front. No, here you go, right behind you. We'll start with the one behind.
Okay, it's not really a question, but I want to say thank you for your hard work you do. That's awesome.
All right, cheers. And that applies to everyone on the team. A lot of work put in by a lot of people, isn't it?
Hold on, wait for the mic. Here it comes.
I just want to know if it's possible, thanks to render to texture, to have an internal bridge of a starship like in Star Trek. So you maybe say for the Polaris, for instance, or a secondary bridge for the Idris. Is it possible with the current tech?
It depends how you define possible. Technically, yes, it's completely possible. You could do it right now. It would work. Frame rate's the issue. If you want 2 renders that are of exactly the same thing, of the same quality, and you want asteroids and fog and all of the post effects we just looked at, then you're going to half your frame rate. So it's very easy to be smart about this stuff and reduce the cost. And for things like holograms, we'll reduce the number of lights. We won't apply certain post effects you don't need. So like a hologram doesn't need anti-aliasing maybe because it's already quite soft and blurry. So there's a lot of scope for doing things. And like say, something like a depth camera or a heat vision, these types of things are much simpler actually, although they might look really cool. They would be much easier, but doing the full rendering pipeline on a full screen would actually be quite intensive on the frame rate. So probably not type of that side, but yeah, it's not a technical question, it's just purely performance and how much we want to be able to let the game scale back to a lower spec system. So that's all we have to keep in mind for that. But it gets asked by design every day, so you're not the only one.
Hey there, I'm from the graphics area myself, and I'm kind of like astonished how much PBR is getting now into game engines. So this is a quite extensive resource drainage, like in terms of how much the cards have to calculate. So do you communicate with AMD and NVIDIA to further develop the PBR-based technology?
Yeah, I mean, when it comes to the physically based stuff, a lot of it's just, to be honest, there's a lot of research online that we tend to look at for like the latest SIGGRAPH or GDC presentations. There's a lot of information out there on how to do the techniques, but when it comes to the performance, that tends to be where we do have contact with the independent hardware vendors like AMD and NVIDIA. Because things like I mentioned that the opaque lighting shader is one giant shader. That is really, really difficult to get to run fast, and that is really difficult to balance across all the different architectures, and that's where you type of need to work really closely with them to make sure that you hit the certain like performance cliffs you have. And you know, if you have one instruction over, you drop like 30% performance. So you need to know where these boundaries are and make sure you fit within them, and it's different for every single graphics card. So yeah, there's quite a lot of cooperation there.
A follow-up on that, do you do research and development on yourself, or is that something where you take it from the developers from AMD and NVIDIA?
Like I say, we don't necessarily take it directly from them, and they do papers at GDC and SIGGRAPH like everyone else does. We take it from whoever's got the best. I mean, we do a lot of stuff internally, like say the optics stuff we showed. That was all in-house. One of our graphics programmers just came up with all of that himself. He'd done a lot of research on all this stuff. But other stuff, like say our area light implementation, we took a lot of the research from that's been done by other game studios and other places like that. But yeah, there's no one source. It's wherever the information is, you know, and it's quite open in game development. A lot of people are happy to share, just like we're showing the guts of our game here. It's quite open. So, Jeff?
He's coming.
A follow-up to the render-to-texture question. So you mentioned that like doing some sort of VR cockpit would be like too much of a strain on the system, but what's the extent of it? Like, for example, we've seen on the RSI Explorer armor, it has like this camera-looking thing mounted on the shoulder. So for example, like sending an away team and having like their point of view displayed in the cockpit, would that be like possible at all? So I mean, so you said it's possible, but would it be reasonable?
I'd have to see the actual case to say yes or no. I'm not the designer, and I don't know. We have to. Sometimes we just run this stuff and just test what the performance is. You never know, and you got like 100 different graphics cards you need to test on. But generally, the advice we've been given to designers, we've got a page type of showing what is likely to be possible and what's not. But generally, if it's any type of constraint on the scenario, it means we can probably do it. So, you know, if I'm in a certain room and it doesn't have too many windows or any windows, I can probably get a view of somewhere else fine, because that room can be made to budget, you know, to take up a certain number of milliseconds in the frame, and then you're free to do the rest of the frame. But if you're in an open environment with windows and you can see asteroids, planets, and everything, and then you want to look at another view of another planet and another set of asteroids, that's what we can't do. So as long as there's a constraint either on the main scene you're studying or the other scene that you're looking at, then that type of what dictates. So it's a bit of a balance act. So it depends where you are and what you're looking at. I hope that answers.
We had someone up front.
Yes. You said there was a lot of strain on the CPU. I was thinking, is there a CPU you would recommend, one with more threads, 8, 12?
No, not particularly. I can't say one or the other. I mean, multi-core is just the key, though. Like, going wide is the direction we're going, the way that everyone is going. Obviously, the higher-end CPUs, like i7s and i9s, there's plenty of bandwidth there, and we're doing our best to fill that. So, yeah, I mean, the single cores, they can't. You could never compete on a single core. I mean, nobody has single cores now, but there's physical limitations that make it extremely difficult. So, going wide is the way. But in terms of a particular model, not particularly, no.
We have time for one more quick question.
Most games I played recently using fake mirrors, like Prayer, for example. Would it be possible, or maybe that's the wrong question, would it be doable without tanking the frame rate to use real mirrors?
Sorry, can you repeat that? I couldn't quite hear. It's a bit. Can you go closer to the mic?
Most games using fake mirrors today. Would it be possible to use a real mirror image without tanking the frame rate too much?
Again, it goes back to the original answer. Yeah, to the last question. Yes, we can do a mirror. It's not. We actually have to do a little bit of work because a mirror isn't like a camera. It's actually the fact that it flips the image. There's something you have to do inside the rendering. You have to type of invert and reverse all the geometry to get it to flip correctly. But it is technically possible. It is something we'll want to do. But again, it's the constraint question. If you're stood on the bridge of an Idris or something, and then you want a mirror there, next to the captain's seat that's going to reflect the rest of the Idris and outside, then no. If you're in a bathroom somewhere, maybe, yeah, that's completely achievable.
Cool. Well, thank you, Ali, for your time.
Cheers.
Thanks for everybody.
All right, thanks, guys.